3 talks today, 2 from the applications track, and 1 from the main track, which was an honorable mention for the Outstanding Paper Award. So the first talk is a novel priority rule heuristic, learning from Justification, and Frits de Nijs is going to be presenting.
Thank you for the introduction. Indeed, I'm going to be presenting a novel priority rule heuristic, and this research is actually my master thesis research. So I'm going to be presenting what I've been doing like in 6 months' time to investigate a project scheduling. So the model we're using and discussing today is the resource-constrained project scheduling problem, in which we're trying to find a schedule for a set of activities, and we need to finish all activities to finish the project. So we can't say, okay, activity 3 doesn't need to happen. The activities we're scheduling might also have precedences, so a sequence in time, where activity 1 needs to finish before activity 2 can start, and activity 2 needs to finish before activity 3 can start. Of course, activities have a set duration, and that's also given by the length of the box. So you can see activity 3 takes more time than activities 1 and 2. Of course, it's a resource-constrained problem, so we also have a resource cap and resource usage. Now, the resource cap indicates a kind of renewable resource. So if we imagine that we have tools like hammers, we might have 2 hammers available, but since activity 2 uses both of them at the same time, it cannot actually run in parallel with any of the other tasks. So that's the idea behind the cap, and the resource usage, that's given by the height of the boxes. Now, of course, we don't want to plan for just one resource. We might have many resources. And the objective is to find a schedule that minimizes the make span of all activities being finished. So it minimizes the time it takes to finish all activities. So we might try to schedule activity 4 in parallel with activity 3, because that would still fit, and then you'd have the shortest possible schedule in this case. Now, this is a very well-studied problem. So people have been researching this since the 60s or even earlier, and there have been many heuristics proposed for this problem. And one of the nice things about this domain is that there's actually very established methodology. So there's a test set that's being maintained by Klos, and also what he does is he publishes papers in which he compares lots of these algorithms. So it's like a survey on how well these algorithms perform, and invariably this leads to kind of an easy way to see how the algorithms compare. Now, this sort of state of the art gives us lots of advantages, right? We have an equal test set, so everyone's using the same problems. We have equal methodology, which means that everyone is doing the same process. We can compare the results, but this also leads to risks. So we might be overfitting on the test set. So because everyone uses the same test set, nobody questions maybe if this test set is hard enough or easy, or maybe it's not missing a certain parameter aspect. And it also leads to a focus on kind of competition. So everyone wants to have an algorithm that they can publish, so it has to be the fastest one in the table. And of course, this leads to maybe no real improved understanding. People are just chasing the next guy that's going to publish, right? So with that in mind, I want to highlight something in this table that was set at the starting point of the research. It seems like all of the really good performing algorithms use forward-backward improvement. Now, this technique is a post-processing technique introduced in 2000 that is like a greedy heuristic, able to improve a generated schedule. Now, it seems like if you don't use this technique, you're not going to end up in the top of the list. But why does it work so well? So our research question that we investigated was, how does this FBI post-processing technique improve these results so much, even though it's using a simple greedy algorithm? And our investigation further was, can we do this study like in a very structured scientific way, so in a very empirical research process. Now, first I should explain the algorithms that are behind this, right? So FBI uses this well-known heuristic called the serial schedule generation scheme that needs a sort of sorting of the activities in order to generate a schedule. From this sorting of activities, it selects the first activity that it can, that's eligible to be started, and it schedules it as early as possible in the schedule being generated. After that, it updates the set of eligible activities and proceeds until there are no more activities to schedule. So I have an example of this. Suppose that we have a heuristic where activity 4, it should be scheduled first, and then activities 1, 2, and 3. In this case, we have that activities 1 and 4 are eligible. After all, they don't have any predecessors that are not yet scheduled. Now, since activity 4 comes before activity 1 in the list, it should be scheduled first. Then only activity 1 is eligible, because activities 2 and 3 are waiting on it, and it is also scheduled at the earliest possible time. Now you can see that this process will continue where activity 2, since it can't run in parallel with activity 4, needs to be shifted to time 3. And finally, activity 3 can then tack on at the end. So this is the serial SGS, but it's important to realize that there's also a parallel variant where it will try to schedule all of the eligible activities at a certain time slot. So it starts at time 0 and then says, okay, activities 1 and 4 are eligible. 4 should be scheduled first, and then activity 1 is scheduled. And then I move to the next time, which is time 1. And at that time, actually, there is no way to schedule activity 2 because it would take too much resources. So I go to time 3, and then again, I sort of parallelly build up this stack of activities. So these are two greedy deterministic algorithms that nevertheless produce decently good schedules, provided that your heuristic gives you a good sequence. Now, FBI makes use of this algorithm in 2 passes. So the idea behind FBI is that sort of the tasks that have this slack, this space ahead of them, they consume their resources too soon. They're sort of early in the schedule. Now, what FBI does is it uses the serial SGS to move these tasks, all of the tasks, to the latest start time. And in the backward pass, it makes use of the freed resources to make the schedule shorter. So to also move through this process with an example, consider we get the schedule that we just generated as input. Now we apply the serial SGS, but first we reverse the precedences between activities. So now activity 3 needs to be started before activities 2 and 1 can start. Now we also use the decreasing finish times of input schedules as the heuristic. So activity 3 finishes last, so it should get the highest priority, then activity 2, then activities 4 and 1. Now, we just apply the same serial SGS sequence to these heuristics and the ordered tasks, and we get as output that activity 3 is scheduled first, then activities 2 and 4 are eligible, so activity 2 is scheduled. Now activity 4 can be scheduled in this gap, because that's left open. And finally, activity 1 can be put at the end of the schedule. So now we have a shorter schedule, except that it's in the wrong order, right? So the precedences are reversed. So the backward pass does exactly the same thing as the forward pass, but applied to the output you got from the forward pass. So the heuristic now tries to take the latest finish time, so activity 1 is the last to finish, should be scheduled first. Then activity 2, and then 3 and 4 have a tie. So the tie breaking is done randomly. So you just pick one of them, it doesn't matter, they're both equally important. Now again, same process. Activities 1 and 4 are eligible, but 1 is to be scheduled first. 2 and 4, 2 to be scheduled first, and so on, until finally we have our output schedule, which is, in this case, the optimal schedule. So we can imagine that FBI does this justification, right? It pushes all of the tasks to the right, justifying them completely to the right side of the schedule. So the center of gravity, if you will, of the schedule goes as far as possible to the right, and then in its reverse pass, in its second pass, it brings everything back to the left side, then thereby justifying everything all the way to the left again. So this algorithm already existed. It works very well. But it has a kind of strange operation, right? So you have this serial SGS, which you generate the schedules with, but it's also inside this post-processing technique that works really well. So what's the idea behind that? And to study that, we try to come up with hypotheses on its operation, but to do that, we first needed to investigate how its performance depends on the input characteristics. So to do so, we had two questions that we wanted to investigate. In the first place, well, what is the impact of the type of schedule that we put in here? Does it depend on the SGS that we use? So if we put in a serial SGS or a parallel SGS as generator for the first schedule, will that make a difference to the performance of FBI? And the second thing we were going to explore is, well, actually we've seen that this backward schedule with the precedence in the wrong order is still feasible if you just flip the order of the precedences. So you don't actually need the second pass to get a feasible schedule. But do you need a second pass for the good performance, right? Does it depend on having two passes in order to work? So those were the questions we investigated. And to do so, we made an experimental setup where we compare the make span of the schedules that we generate as a sort of percentage of the best known schedule. So since we don't have the ability to compute the optimal schedule of our test set, which contained about 20,000 instances, we compare with the best one we found on all of our experiments. And we generated our test set along the parameter called order strength. Now, order strength is how temporally constrained the instance actually is. So order strength measures the number of precedences, including those that are implicit from the precedences between tasks, divided by the maximum possible. So it's a ratio of constrainedness. Now, if you have like a complete graph where every task depends on some other task, you have an order strength of 1. And if you have a task without project without precedences, then you have an order strength of 0. And real projects have been found to have something like 2 to 5 predecessors transitively. So in 50 activities, which is the size of our test set, that should give you an order strength of 0.08 to 0.2. So quite low, actually. Now, our observations on the performance of FBI were along this test set using the parallel and the serial SGS, where the red line indicates just the schedules you'd get if you run the parallel SGS with the latest finish time heuristic, or the serial SGS with the latest finish time heuristic. And you see that actually the performance between the two systems is not that different, although, as expected, actually the parallel SGS produces slightly shorter schedules. Now, the green line indicates the FBI where you just perform one pass, so you just justify everything to the right and then flip the precedences to get a feasible schedule. And the blue one is the actual operation of the post-processing box entirely. So that's the post-processing as you would use it in a production algorithm, let's say. Now what we see is that there's a strong performance on the parallel SGS. So even one pass improves the parallel SGS solutions much better than the serial SGS. So a single pass is sufficient for large improvements. The second pass, of course, still improves the matters, but it's not like only having the first pass doesn't do anything. So this led us to pose hypothesis on why. So try to find an explanatory idea behind its operation that gives this performance. Now, one thing that was known already is that the serial SGS generates schedules that are active. So these are schedules that belong to the class of active schedules. And now what an active schedule is not so important, but what is important is that the parallel SGS generates schedules that are non-delay, which is a subset of the active schedules. And in particular, the active schedules, there's always going to be an optimal schedule that is active, but it's not guaranteed that there's an optimal schedule that is non-delay. So what we hypothesize is that FBI performs a kind of function where it takes a non-delay schedule and transforms it into a delay schedule, so into a complement of this non-delay class into the active space. Since it's using the serial SGS, it will generate active schedules, but we hypothesize that in particular it will generate schedules that are not non-delay. So how would we test that? I mean, how would you test that it actually generates these delay schedules? Well, what we came up with is that if there's a parallel SGS generating your schedule, then you will take this FBI function, which happens on the first transition to the serial SGS. Now, suppose our input is instead the serial SGS, then the first operation, we replace it with a parallel SGS, then you will see that you get this transition, which we hypothesize is important for the performance of FBI, on the transition from the parallel to serial in the second FBI pass. On the other hand, if we replace everything by parallel, we would stay in the non-delay space. So that would give you bad performance. So we tested these predictions on the performance of FBI by replacing the algorithm used inside the FBI procedure. So either SGS to either SGS to parallel SGS keeps you in non-delay space, so that should be bad. And the serial to the parallel back to the serial, that should give you the transition from non-delay to delay, and that should be good performance. So here are the results, and indeed we can confirm that if you end on the parallel schedule generation scheme, so that's the yellow or the blue instances, we see that there's very little improvement on the input schedules. On the other hand, if the input schedule is generated by the serial SGS, and we first transition to parallel and then to serial, which is the green line, we see that we get better performance than the FBI using serial in both cases. So it's actually also confirmed that this is sort of better performance than you would expect from FBI. So at the same time, there should be another effect behind FBI, because we've seen that doing parallel, you still get an improvement. So we also hypothesize that these priorities are somehow special. So the schedule that you put in is actually a better heuristic than the heuristics we have. So we sort of hypothesize that the longest chain in your schedule has suffered the most delay. So the tasks that are at the end of the schedule were kind of critical. They were part of these peaks and they were hard to schedule, so they ended up at the end of the schedule, thereby getting a very high priority in FBI. So an initial schedule is sort of a good estimate of the delay of the activity. Now, if we want to make this delay sort of a priori into a priority heuristic, then we can try to use the early start schedule as an estimate of a feasible schedule. Now, the early start schedule is not feasible, but we do have peaks in the early start schedule that we can use to estimate how much tasks are delayed. So if we have a peak, then this height of that peak sort of indicates how much space you would need to delay tasks by. Now, if you multiply that by the average duration, you get kind of a block that you need to translate from vertical to horizontal, where inside that block, your usage relative to the capacity indicates how much you are pushing this peak up. So how likely that peak is to influence your position in the schedule. Now, of course, just your delay is not enough. You need to put it relative to the early start schedule. So if we're looking at the delay of task 1, then it's actually its delay plus its duration plus the delay of the subsequent tasks. Because actually the subsequent tasks might be very important, even though activity 1 is not important at all. But then still you would want activity 1 to be scheduled because it's holding up the tasks that are likely to get delays even more. So this is the idea behind the resource profile rule. Now, if what we expect is that this should do the same as FBI, then the priorities of the resource profile rule should be similar to the priorities that FBI generates, at least more similar than the heuristics that we already know. So in this case, we compare the priorities that go into FBI with the priorities that go into resource profile rule on terms of their distance to each other. So a distance of 0 would give you the priorities of FBI, and then the latest finish time rule sort of starts converging to FBI the more precedences you have. Of course, if you have order strength of 1, you don't have to schedule anything, so that makes sense, I think. On the other hand, the resource profile rule actually gets priorities that are closer to the FBI priorities. So actually we can sort of get evidence that also FBI uses this concept of delay importance. Now, of course, just being closer in priority is not important. What's important is that the similar priorities then also should lead to better performance than the existing heuristics. And what we find here is that without applying FBI, using our resource profile rule, we get indeed shorter schedules than the latest finish time rule. But after applying FBI, the difference is not so great, except in the very lowest range of order strength, which is of course where the more realistic projects are. So our conclusions are that the transition from non-delay to delay is necessary for FBI performance, and it's possible to estimate these FBI priorities from the early start schedule. And finally, that this resource profile rule works well if the order strength is low. But actually, the most important conclusion is not on what we found as results, but rather that this empirical evaluation of algorithms really works well to get new understanding and faster algorithms. Thank you.
We've got time for a quick question.
Okay, so given how you ended, how would you change this to make it better, given what you've learned?
How would I change which procedure exactly?
The FBI or whatever heuristics you're using? Because you ended by saying that this tells us a lot about how the algorithm's working, how the heuristic is working, and that helps us to improve algorithm development. So the obvious question then is, how would you go from here to improve algorithm development further?
Right. So, of course, the general procedure of empirical evaluation of algorithms can be applied to more than FBI. So if you're going to look into, for example, a meta-heuristic, then it would also, in that case, be important to not just say, okay, I'm going to improve this meta-heuristic by changing, let's say, the sample size or some ad hoc procedure. What I think is important that before you make changes to an algorithm or propose a new algorithm, you first reason about why this algorithm should be good. So why what you're going to do is going to give you a better performance. So try to first come up with a hypothesis that if I change this, then I will get a type of effect, like a change of the class of the schedule, for example. And then not just in experiments test that your performance is better, but also that you actually can see this effect that you predicted, or any other effects if it's not observable, then the effects, then you might be able to predict different kind of behavior.
Okay, thank you.